What is a limiting reagent or a limiting reactant? Let us try to understand that in this video. Let us imagine that we are assembling bicycles. And we need a lot of components to assemble a bicycle, but for our discussion, let us consider only these three components. And imagine that we have sufficient number of other components like pedals, chains, etc. to assemble the bicycles. And we all know that each bicycle has one saddle or seat, one handlebar and two wheels. So, to make one bicycle, you need one saddle, one handlebar and two wheels. Or in other words, in each bicycle, these three components are present in the ratio of 1 to 1 to 2. Now, if I have two saddles, two handlebars and four wheels, how many bicycles can I assemble using these components? Now, by looking at these quantities, the first thing I understand is that they are in the ratio of 2 to 2 to 4. If you divide each of these terms with 2, then the ratio becomes 1 to 1 to 2, same as the ratio in which these components are present in a bicycle. So, here I have the components in the correct proportion. Now, if the components are in the correct proportion, then how do we figure out the number of bicycles we can make using these components? Easy. You can figure that out by using any of these three relationships. You have a relationship between the number of wheels and the number of bicycles. You have a relationship between the number of handlebars and the number of bicycles, and you also have a relationship between the number of saddles and number of bicycles. You can use any of these three relationships to figure out the number of bicycles you would make. It doesn't matter which relationship you pick, it is completely your choice. Now I pick the number of wheels to answer this question. Here we have four wheels, right? With two wheels we can make one bicycle. So obviously with four wheels we can make two bicycles. And you would get the same answer even if you go by the number of handlebars or the number of saddles. Give it a try. With one handlebar we can make one bicycle. With two handlebars we can make two bicycles, right? We got the same answer. And you will get the same answer even if you go with the number of saddles. So what I'm trying to say here is, if the components are in the correct proportion, are in the correct ratio, then we can estimate the output of the bicycles by using any of these three relationships. We don't need all the three relationships. Any one relationship is good enough, and we don't care which relationship is used. You can pick any relationship that you want, you will always get the same answer. Now, let us say I have 20 saddles, 20 handlebars and 40 wheels. Then how many bicycles can I produce using these components? Again, I would first look at the ratio of their quantities. It is 20 to 20 to 40. If you divide each of these terms with 20, again the ratio becomes 1 to 1 to 2, same as the ratio in which these components are present in each bicycle. Therefore, they are in the correct proportion or the correct ratio. So, I can figure out the number of bicycles using any of these three relationships. Now, let us go with the number of saddles. There are 20 saddles, right? You can make one bicycle using one saddle, and if you have 20 saddles, you can make 20 bicycles. And you will get the same answer even if you go by the number of handlebars or the number of wheels. Now let us take a third case where I have 20 saddles, 18 handlebars and 16 wheels. Now using these components, how many bicycles can I assemble? Now if you look at the ratio of these quantities, it is 20 to 18 to 16. If you divide each of these three terms with 20, you would have 1, 2, 18 over 20 is 0.9 and 16 over 20 is 0.8. So here I have these three components in the ratio of 1 to 0.9 to 0.8. But the correct proportion is 1 to 1 to 2. This is the ratio in which these components are present in each bicycle. But here I have them in this ratio. So they are not in the right proportion, in the correct ratio. Then how do I figure out the number of bicycles I can make using these quantities? Like before, can I use any of these three relationships to figure that out? Let us try it out. Let us start with the number of saddles. We have 20 saddles, right? With one saddle, you would make one bicycle. So with 20 saddles, you must be able to make 20 bicycles. So if you go by the number of saddles, the answer you would get is 20 bicycles. But to make 20 bicycles, you need 20 handles, right? For each bicycle, you must have one handle. So for 20 bicycles, you must have 20 handles. But you have only 18. 2 less than the required quantity. So that obviously means this answer is wrong. You cannot make 20 bicycles though you have 20 saddles. The reason being, you do not have sufficient number of handles. So first thing we understood is, if the ratio of the quantities is not same as the ratio in which these components are present in a bicycle, then you cannot use any of these three relationships to figure out the number of bicycles you can make. We tried with the number of saddles and we got a wrong answer. Then let us go with the number of handlebars to see if we get the right answer in this case. With one handle, you can make one bicycle, and with 18 handles, you can make 18 bicycles. So if you just go with the number of handles, the answer is 18. And we have 20 saddles, 2 more than required. So we are good with the number of saddles, right? But look at the number of wheels we have. We have 16 wheels. And to make 18 bicycles, because each bicycle needs 2 wheels, for 18 you need 36 wheels. But here we have only 16. There is a huge shortage of the number of wheels. 20 short of the required number of wheels if you go by the number of handlebars. That means this answer is also wrong. Then we are left with the number of wheels. How many wheels do we have here? 16, right? And you know, to make one bicycle, you need 2 wheels. So using 16 wheels, you can make 8 bicycles, not 18, 8 bicycles. And to make 8 bicycles, you need 8 handlebars and you need 8 saddles. So we can use all the 16 wheels to make 8 bicycles, and in that process we are using up 8 handlebars and 8 saddles. And that is the correct answer, because we have sufficient number of handlebars and saddles to make 8 bicycles. And at the end of assembling all the 8 bicycles, you will be left with 0 wheels and 10 handlebars and 12 saddles. So these are the leftover components. Remember, because we have extra handlebars and extra saddles, with an intention to use them up all, you cannot throw extra saddles and handlebars in each bicycle. It doesn't make sense, because you have 10 extra handlebars and 12 extra saddles. After making 8 bicycles using all the 16 wheels, you cannot say that I will put 1 handlebar extra on each bicycle and probably 1 saddle as well, 1 extra saddle as well. It doesn't make sense. So whether these quantities are in the right ratio or not, the composition of the bicycle is going to be the same. It is 1 to 1 to 2, 1 saddle, 1 handlebar and 2 wheels. So this is not going to change with the quantities that you have with you. Remember that. So what we understood here is, if the quantities of these components are not in the correct proportion, then the output of our assembly line, that is the number of bicycles that we could assemble, is determined by that component that is most deficient. So if the quantities that we took are not in the correct proportion, that means it is not same as the ratio in which these components are present in each bicycle, then the output of our production is determined by the component that has the most shortage. In this case, we are able to make only 8 bicycles, though we have 18 handlebars and 20 saddles, is because we have only 16 wheels. So the output is solely determined by the number of wheels we have in this example. That is why this component is the limiting component, because this is limiting the number of bicycles that we are able to produce. Therefore, if the quantities are not in the same proportion in which they are present in each bicycle, then to figure out the output of our production, you have to identify the component that has the most shortage, because it is that component that determines the output. That is the limiting component. Now, how do we identify the limiting component? Just look at their ratio and compare this ratio with the expected ratio. You can figure out the limiting component by comparing these two ratios. Here, for each bicycle we need 2 wheels, but here we have only 0.8 wheels. So here the shortage is 1.2 wheels per bicycle, whereas here we have 1 and 0.9 for handlebars. That is, for each bicycle you need one handlebar, but we have only 0.9, so the shortage is 0.1. Even here there is a shortage, but the shortage is less here and more here. And here, in case of saddles, both are ones, so there is no shortage. So you can easily identify the limiting component by comparing the actual ratio with what it should be. Now we are going to use this analogy to a chemical reaction. Hope that makes sense. Now let us consider the synthesis of water from hydrogen and oxygen. This is the equation for that chemical reaction. It is not balanced, obviously. We have 2 oxygen atoms here and only 1 on the right hand side. To balance it, we have to apply law of conservation of mass to this equation. And upon balancing, you would have 2H2 plus O2 gives rise to 2H2O. And the coefficients you see in the balanced chemical equation are known as stoichiometric coefficients, and their ratio is 2 to 1 to 2. Now what do these stoichiometric coefficients tell us? What is this ratio? This is the simplest ratio between the quantities of reactants and products involved in this reaction. In a previous video, I explained many interpretations of these stoichiometric coefficients. One of those interpretations is molar interpretation. And according to the molar interpretation, this ratio means for every mole of oxygen that you take in this reaction, you must take 2 moles of hydrogen to completely combine with it. That is, if you do not want to have any leftover oxygen at the end of the reaction, then for every mole of oxygen that you take, you must take 2 moles of hydrogen. And if you take hydrogen and oxygen in this proportion, then at the end of the reaction, there will be no leftover hydrogen or oxygen, assuming the reaction goes to completion. And in that process, for every mole of oxygen that you took, you would get 2 moles of water. That is what these stoichiometric coefficients mean. So they tell the proportion in which the reactants must be mixed so that they completely combine with one another without leaving any reactants left behind, without any wastages. Now let us say I took 2 moles of oxygen to carry out this reaction. And to completely combine with 2 moles of oxygen, we need 4 moles of hydrogen. So if you take hydrogen and oxygen in these amounts, then they would completely combine with one another without leaving any hydrogen or oxygen behind, assuming the reaction goes to completion. Now my question is, how do I know the amount of water formed in this reaction? Now to figure that out, you can use either of these 2 relationships, because the ratio in which hydrogen and oxygen are taken is 4 to 2, that is 2 to 1, same as the ratio of their stoichiometric coefficients. So they are in the expected proportion for them to completely combine with one another. So we can figure out the amount of water by using a relationship between the number of moles of oxygen and water or the number of moles of hydrogen and water. Now, using the number of moles of hydrogen and water, what answer do we get? If you take 2 moles of hydrogen, you would get 2 moles of water. If you take 4 moles of hydrogen, you would get 4 moles of water. And you would get the same answer even if you go by this relationship. Because if you take 1 mole of oxygen, you would get 2 moles of water. Because you have 2 moles of oxygen, you would get 4 moles of water. See, we got the same answer either by using this relationship or this relationship. It did not matter at all. That is because the quantities of hydrogen and oxygen that I took are in the same ratio as their stoichiometric coefficients in this equation. Now let us take another case in which we mixed 2 moles of hydrogen with 2 moles of oxygen, and we want to know the amount of water formed in this case. By looking at these amounts, you understand that they are in the ratio of 1 to 1, and this ratio is not same as the ratio between their stoichiometric coefficients. The ratio between their stoichiometric coefficients is 2 to 1, but the number of moles of hydrogen and oxygen mixed in this case are in the ratio of 1 to 1. So this case is different from these two cases. In these two cases, the number of moles mixed are in the same ratio as their stoichiometric coefficients, but that is not the case here. Is this similar to this example where we had 20 saddles, 18 handlebars and only 16 wheels? I think so. See, these stoichiometric coefficients tell the ratio in which they must be combined so that they completely combine with one another without leaving behind any leftovers, provided the reaction goes to completion. But that does not mean that I must always mix them in that proportion. If I don't care about wastages or leftovers, I can mix them in any proportion that I want, and that's exactly what I did here. I mixed 2 moles of hydrogen with 2 moles of oxygen. So in this case, how do I estimate the amount of water formed? Can I use any of these two relationships to estimate the amount of water formed the way I did in these two cases? Let us give that a try. Let us go with the number of moles of oxygen. This relationship tells that if you have 1 mole of oxygen, you would get 2 moles of water. Here we have 2 moles of oxygen. That means you must get 4 moles of water, right? So the answer you would get by using this relationship is 4 moles. Now let us see what answer we would get by using this relationship between the amount of hydrogen and the amount of water. If you have 2 moles of hydrogen, you would get 2 moles of water. And here we have 2 moles of hydrogen, so you must get 2 moles of water. So we got a different answer by using the amount of hydrogen from what we got by using the amount of oxygen. Then which of these two answers is correct? Let us see. See, though we have 2 moles of oxygen here, to completely combine with this oxygen, we need 4 moles of hydrogen. But here we have only 2 moles of hydrogen, less than what is required. Therefore, all the oxygen that you took is not completely combining with the amount of hydrogen available here. So that means some oxygen is left behind unreacted. Therefore, this answer is wrong and this answer is correct, because to completely combine with 2 moles of hydrogen, you need only 1 mole of oxygen, but here you have 2 moles of oxygen, more than what is required to completely combine with 2 moles of hydrogen. So out of 2 moles of oxygen, only 1 mole of oxygen is combining with 2 moles of hydrogen, and 1 mole of oxygen will be left behind. So at the end of the reaction, assuming that it goes to completion, there will be no leftover hydrogen and there will be 1 mole of oxygen left behind. Therefore, because you have sufficient oxygen to completely combine with the amount of hydrogen that you took, the amount of water estimated or calculated using the amount of hydrogen is correct. And it is the amount of hydrogen that is determining the amount of water formed in this case, because that is present in lesser amount. That is why this reactant that is present in lesser amount is called the limiting reagent or limiting reactant, because it is this reactant that imposes a limit or a restriction on the amount of product formed. So, if the amounts of reactants taken are not in their stoichiometric proportions, that is, not in the ratio of their stoichiometric coefficients, then you have to first identify the limiting reagent to estimate the amount of product formed, because it is this limiting reagent that imposes a restriction on the amount of product formed. Now, how do we identify the limiting reagent? Simple. Compare the ratio of the amounts taken with the ratio of their stoichiometric coefficients. The ratio of the stoichiometric coefficients of hydrogen and oxygen is 2 to 1. That is, for 1 mole of oxygen, there must be 2 moles of hydrogen to completely combine with it. But here, for each mole of oxygen, I took only 1 mole of hydrogen. So, it is the amount of hydrogen that is less than required. So, this is the limiting reagent. The reactant that is in shortage is the limiting reagent. Therefore, in this case, to calculate the mass of water formed, you have to use the relationship between the number of moles of the limiting reagent and the number of moles of product. So, the calculation obtained using this relationship is correct and this would be wrong in this case. So, I hope that gave you an idea about what a limiting reagent is. And when we work out a couple of examples, you would gain more clarity. Now, before we move on to the examples, let me highlight what we discussed so far. Limiting reagent is the reactant that has the most shortage. Secondly, at the end of the reaction, assuming that the reaction goes to completion, there will be no leftover limiting reagent. All the limiting reagent would have reacted, leaving nothing behind. Then, at the end of the reaction, assuming that it goes to completion, the excess reactant will have some leftover. See, in this case, there is no leftover hydrogen, but there is 1 mole of oxygen that is left behind at the end of the reaction. And finally, To estimate the amount of product formed, you have to identify the limiting reagent and use the relationship between the limiting reagent and the product. In this case, the limiting reagent is hydrogen, and we used the relationship between the number of moles of hydrogen and the number of moles of water in the balanced chemical equation to estimate the amount of water, because it is the limiting reagent that imposes a restriction on the amount of product formed. Now we are ready to do some examples. Here comes our first question. It says acetic acid is industrially produced by bubbling oxygen gas in acetaldehyde using manganese acetate as catalyst under pressure at 333 Kelvin. If in the laboratory the same reaction is carried out between 22 grams of acetaldehyde and 16 grams of oxygen, what is the mass of acetic acid produced and the mass of excess reagent remaining at the end of the reaction? Before we answer this question, let us take a look at a slightly different question. This question says iron is extracted from its chief ore hematite by reducing it with carbon monoxide in a blast furnace. Then how much iron can be obtained from 100 kilograms of the ore? And we are given the balanced chemical equation. And by looking at this equation, you understand that there are two reactants here. Hematite is nothing but ferric oxide. Here we are given only the mass of the ore taken and nothing is said about the mass of carbon monoxide available, yet we are asked to calculate the mass of iron produced. How can we answer such a question? Here you have to assume that there is sufficient amount of carbon monoxide to react with all the ferric oxide we took, all the ore we took. Sometimes that is explicitly stated, sometimes you have to figure that out. So if you are given the mass of only one of the reactant, then you have to assume that the other reactants are available in sufficient quantities for this reactant to completely react without leaving anything behind. With that assumption, you can use the relationship between these two to calculate the mass of iron produced. But that is not the case here. If you look at this balanced chemical equation, again you understand that there are two reactants, and here we are given the mass of both the reactants. And we are asked to calculate the mass of acetic acid produced. Here also there are two relationships, right, between the number of moles of oxygen and acetic acid and the number of moles of acetaldehyde and acetic acid. Here you cannot say that I would assume that these masses of acetaldehyde and oxygen would completely combine with one another. Therefore, I will use either of these two relationships to estimate the mass of acetic acid produced. You cannot make that assumption here. So what should I do? First, I have to make sure that or verify that the given amounts of the reactants are in the correct proportion for them to react completely with one another without leaving anything behind. If they are, then you can use either of these two relationships to estimate the mass of acetic acid. If not, then the amount of acetic acid produced is determined by the reactant that is present in lesser amount, and that reactant is called the limiting reagent. So you have to identify the limiting reagent and use the relationship between the number of moles of the limiting reagent and the product to estimate the amount of product formed. So how do we do that? Simple. Convert the given masses into the number of moles and take the ratio of the number of moles taken and compare it with the ratio of their stoichiometric coefficients. The ratio of their stoichiometric coefficients is 2 to 1. Now what is the ratio of the number of moles? We are given masses. To get the number of moles, you have to divide the given mass with its molecular weight expressed in grams. For acetaldehyde, I think the molecular weight is approximately 44, expressed in grams is 44 grams. And the number of moles of oxygen is, again, divide the given mass with its molecular weight in grams. Here we are talking about oxygen molecules, so its molecular weight is 32, expressed in grams is 32 grams. Now what is the ratio between these two? This is half, this is half. So the ratio is 1 to 1. This is the ratio of the number of moles that are taken, and the ratio should be actually 2 to 1 for them to completely react with one another. Here we have the same number for the number of moles of oxygen, but we don't for the number of moles of acetaldehyde. For 1 mole of oxygen, we should have 2 moles of acetaldehyde for them to completely react with one another. But for 1 mole of oxygen, I took only 1 mole of acetaldehyde. So what is present in lesser amount? Acetaldehyde, right? So acetaldehyde is the limiting reagent. So the amount of acetic acid produced is determined by this limiting reagent. So you have to use the relationship between acetaldehyde, that is the number of moles of acetaldehyde, and the number of moles of acetic acid to answer this question. So if you have 2 moles of acetaldehyde, you would have got 2 moles of acetic acid, right? But here we have only half mole of acetaldehyde. Then how much acetic acid would you get? Simply half mole, right? So you would only get half mole of acetic acid from half mole of acetaldehyde. Then how do you get the mass of acetic acid produced? You have to multiply the amount of acetic acid produced, the number of moles of acetic acid with the unit mole, with its molar mass. What is the molar mass of acetic acid? Is it 24 plus 4 plus 32? 60. So its molar mass is 60 gram per mole. And upon simplification, you would get 30 grams for the mass of acetic acid produced. Now we have to calculate the mass of the excess reagent remaining at the end of the reaction. By the way, what is the excess reagent in this reaction? We first figured out that these masses are not in the right proportion for them to completely react with one another. Secondly, we identified that acetaldehyde is the limiting reagent. Then that obviously means oxygen is the excess reagent. So we have to figure out the mass of oxygen left behind at the end of the reaction. See, we have started with 22.0 grams of acetaldehyde and 16 grams of oxygen, and there is no acetic acid at the start of the reaction. Now, because acetaldehyde is the limiting reagent, by the end of the reaction, all the acetaldehyde we took would have reacted, leaving behind nothing. And in this calculation, we found that 30 grams of acetic acid is produced. So when 22 grams of acetaldehyde completely reacted with sufficient oxygen, we got 30 grams of acetic acid. Now, can you apply law of conservation of mass between these three? Because this is a combination reaction. These two reactants are combining to form a single product. Therefore, the mass of acetaldehyde and oxygen consumed in the reaction must be equal to the mass of acetic acid produced. So let us say X grams of oxygen has reacted. So 22 grams of acetaldehyde has reacted with X grams of oxygen to produce 30 grams of acetic acid. The total mass of the reactants must be equal to the total mass of the product. Law of conservation of mass. Then what will be the value of X? 30 minus 22. 30 grams minus 22 grams, that would be 8 grams. So 8 grams of oxygen has reacted, leaving behind 8 grams. 16 minus 8 is 8. So at the end of the reaction, there will be no acetaldehyde left behind. 8 grams of oxygen will be left behind and you will have 30 grams of acetic acid. By the way, there is another method to calculate the mass of excess reagent remaining at the end of the reaction. That is by using the relationship between the number of moles of acetaldehyde and the number of moles of oxygen. From this equation, we understand that 2 moles of acetaldehyde needs 1 mole of oxygen to react completely. So 2 moles of acetaldehyde need 1 mole of oxygen to react completely. But how much acetaldehyde is reacting in this reaction? We took only half mole and that is the limiting reagent. So half mole of acetaldehyde is reacting. So for half mole of acetaldehyde, how much oxygen is needed? So the number of moles of oxygen needed is equal to half mole multiplied with 1 mole over 2 mole. Then the answer would be 1/4 mole. So to react with half mole of acetic acid, we need 1/4 mole of oxygen for this reaction. What is the mass of 1/4 mole of oxygen? You have to multiply the number of moles of oxygen with its molecular weight expressed in grams, that is 32.0 grams. So that would be 8 grams. So 8 grams of oxygen is required to react with 22 grams of acetaldehyde. But we took 16 grams of oxygen, and if 8 grams has reacted, then what will be the mass of the leftover oxygen? 8 grams.